All right, welcome to my first video on neural networks. So this is going to be an explanation of some of the basics behind deep learning and neural networks in particular. I say level 1 here because I don't want to assume anything about anything that people know. And as long as you have a basic math background, this material should be understandable. All right, so let's get started. So there's a lot of data in this world, and they come in many different forms. We have graphs, we have charts, we have data points on a plane, we have databases, we have curves. But in order to use this data effectively, we have to be able to learn from patterns. And learning from patterns is a very hard problem because you have outliers in the data, you have so many different ways of viewing the data, and so many different ways of having human error interfere in this process. But machine learning is a way to solve all of the world's, or rather, very specific problems using data. So what is machine learning? Well, very simply, you take the data that you have for a problem, and then you plug it into some kind of machine. That machine does some processing, the cogs turn, and you get an output. That output is used to solve some kind of real-world problem. So imagine you're trying to predict the risk of heart disease for Americans. What you need to know is the weight and the height and the age and the gender. All of these factors are your data. You plug it into the machine, and perhaps it outputs a percentage, the risk of heart disease. And you can repeat this kind of same formula for any problem that you can solve using data. Now, what's the connection between artificial intelligence and machine learning, or what is the difference? Well, artificial intelligence is a very big circle that encompasses a lot of different fields. It could include computer vision, it could include robotics, it could include a lot of different things. And machine learning is a much smaller circle within artificial intelligence. Machine learning is primarily concerned with getting computers to learn from data, whereas artificial intelligence may not necessarily be concerned with that. For example, if you're trying to develop an algorithm that can beat someone at tic-tac-toe, that's not necessarily a part of the domain of machine learning, unless you use something like reinforcement learning. But the idea is that artificial intelligence is much broader. And then within machine learning, you have deep learning, which has really been responsible for most of the advances in the field you've seen in the past few years. So I just want to talk about the kinds of advances we've seen. We have self-driving cars, we have AlphaGo beating the world's best Go champion, we have deep fakes that create images that make people believe that the original video wasn't even edited, and you have extremely powerful facial recognition software. So all of these events, all of these accomplishments and milestones were made possible by a lot of hard work in the field of deep learning. So I'm hoping this gets you excited about learning about it. Okay, so what is the best machine learning problem for someone to tackle to learn more about the field? Well, I thought about it a little, and I think the best problem would be to learn how to use a neural network to predict the AND gate operation. So if you're not familiar, the AND gate takes two inputs, x1 and x2. If x1 and x2 are both 1, then the output is 1. All values are either 1 or 0, like a bit. So if either one of x1 or x2 is 0, then the output of the AND is 0. Basically, AND means x1 and x2 has to be on in order for the output to be on. So we're trying to predict the output of the AND operation using data. So we're basically trying to teach the computer how to perform the AND operation from scratch. Well, if we zoom out a little bit, this problem is essentially a learning problem. We're trying to replicate some kind of intelligence, some kind of learning in the computer. So in order to do that, we can take some inspiration from neuroscience and how humans actually do this learning process. Now here is an actual neuron. The important parts are the synapses down there, which connect to other neurons before it. And then we have the axon, which serves as the bridge between the dendrites and synapses, and the dendrites, which is used to pass along the signal to neurons further up. So whenever you are trying to learn something, there's positive reinforcement, there's negative reinforcement. For example, you're trying to learn how to play the piano, and pressing certain keys make you play the song much better. So you want to positively reinforce that behavior. So if we zoom into a neuron in your brain, that means that whatever signal is being fed into your neuron that is responsible for that positive behavior should be positively reinforced. Now, if there are signals that are leading to very bad behavior, very bad results for your piano playing, then those should be de-emphasized, and those signals should get weaker. So this is a very concise explanation of a primitive learning process. We emphasize the signals that help us, and we de-emphasize the signals that don't help us. And this quotation by Donald O. Hebb is really, really important for expressing the fundamental idea behind what I just said, which is that cells that fire together wire together. Meaning that if you have a signal that is contributing to a good result, then you want that signal to be even stronger the next time around, right? Because it's helping you. But if it's not helping you, then it shouldn't become stronger, it should become weaker. So this entire learning process that we've developed in neural networks is really based off of a very fundamental idea that Donald O. Hebb explained early on. So without further ado, let me introduce the perceptron. The perceptron is basically a computational model for a biological neuron. Now, not all of the things in here are exact, faithful duplicates of how an actual human neuron would work, but it is meant to be a model of how a neuron would work. So we have a couple of different things here. We have an input layer where we can see our x1 and x2. Remember, those are inputs to the AND gate. And then we have a bunch of weights. These determine how strong the signal should be. So in order to compute something with a perceptron, all you do is you multiply the inputs by the weights, add them all together, which is what that sigma node is doing, and then pass it through an activation function. And that gives you an output. Now, we have to remember that in order for the perceptron to actually learn, we need to change the signals, right? That's what we were talking about before. We need to change the signals. To change the signals, we have to change the weights. And here we introduce the update rule. Here we have delta wj is equal to eta times y minus y hat times xj. So we're going to see how this update rule plays a role in the computation later on, and it will make more sense as we go through the rest of this slide. So let's just give some concrete numbers to everything. The weights are all set to 0, the inputs are all set to 0, and our eta, which is that squiggly n, is set to 0.2. That's our learning rate. So that determines how fast we learn or how slowly we learn. Kind of like how you would learn in real life, right? So in order to compute the output of the perceptron, we have to do some arithmetic. So like we said, we have to do inputs multiplied by the weights. W0 times 1 is W0, plus W1 times X1, plus W2 times X2, right? And that entire equation, that entire expression, is the output of the sigma node. And then we just pass it through the activation function, which is that unit step function looking node, in order to get our output. So here, we say that the neuron fires whenever the signal is greater than 0.5, and that it does not fire otherwise. So if we actually do the arithmetic here, we see that the weights are all zeros. So we're passing in 0 to the activation function, which means that it's less than 0.5, which means that the perceptron outputs 0. Now, that's good, because for an input of x1, x2 equals 0, the AND gate should be outputting 0. So our perceptron predicted correctly what the output of the AND operation should be. Now let's try another example. What if we set x1 equals 1 and x2 equals 1? Now, we're going to do the same thing. We're going to see what the output of the perceptron is. Well, it turns out that it still outputs 0 this time around. But unfortunately, this is wrong, because if we have both the inputs being 1, the AND operation should output 1, not 0. So the perceptron made a mistake here. How do we fix that mistake? Well, this goes back to the whole idea of learning from your mistakes, trial and error. So we're going to use our update rule. Okay, so notice that we apply the update rule to all the weights. Here, notice that we apply it to W0, W1, and W2. Excuse the error, W1, every index is supposed to be subtracted by 1, so W1 is actually W0, W2 is actually W1. But in any case, we're changing the weights here in order to get a better answer. And if we actually look at one computation, one example computation, we can see how the update rule works. So we have eta, which is 0.2, times y. Now our actual answer should be 1, right? Minus y hat, which is 0, times xj, which is 1. So we're basically getting delta wj equals 0.2, which means that we're making each of these weights stronger. We're making the signal stronger. And that makes sense, right? Because the perceptron actually predicted a 0 when it should have predicted a 1. That means the signal wasn't strong enough for it to fire. So we're going to make the signal stronger so that next time when you ask me the same question, I'm going to get the right answer. Okay, so we've changed the weights. And right now I'm just showing you that all the weights are being set to 0.2. We still have x1, x2 equal 1, and eta is still 0.2. Now, there are usually a lot of iterations of this algorithm in order to get a good predictive perceptron, like a highly accurate one. But for this very simple example, this toy example, these weights are actually correct. So it only took 2 iterations. You can check yourself if you want. Okay, so how can we actually implement this kind of thing in code? So let me go through what you need to do in order to implement a perceptron, and you can try it yourself at home to see just how exciting this kind of machinery is. So I'm assuming you're familiar with Python matplotlib. We have a couple of different snippets of lines of code here. First, we have an output function, and this really simply just does what I described in the last slide. It computes the output of the perceptron, right? W0 times W1 times X1, and so on and so forth. This update function, that's just implementing the update rule. We'll skip the eval line function for now. So the activation function, or the activate function, is literally an implementation of what we described before. Greater than 0.5, fire. Otherwise, don't fire. And then for the next cells on the right, this is just setting up the data. I'm just trying to create all possible values of inputs and creating those lists so that they can be fed into the perceptron. So in this cell 7 right here, what I'm doing is I'm setting epochs equal to 2, and then I'm going to just perform the perceptron algorithm, which basically says I'm going to calculate the output of the perceptron. If I make a mistake, I'm going to update the weights. If I don't make a mistake, then I just move on. And at the end of the 2 iterations, you can print the weights out. You'll see that they're all 0.2, like we discussed before. So going back to cell 4, this eval line function is actually plotting the line that will separate points from 2 different classes. So this may not make much sense at first, but when we're trying to do a classification problem like this, meaning we're trying to separate one class of inputs from another class of inputs, we can view that as trying to find a separating line that will divide one region into 2 regions. So what we're really doing is we're trying to divide a set of points into class 1 and class 2. And the Perceptron algorithm is actually just finding the best line that will divide those 2 classes. So the eval line function just helps us plot that line. And this will make more sense in this next slide. So notice that I'm just plotting the possible inputs to the AND gate here. 0, 0, 0, 1, 1, 1, and 1, 0. So notice that, one more thing to note is that if the AND gate returns a 1, then I color it green. Otherwise, I color it 0. So we have 2 different classes of points here, right? One where the output is 0 and one where the output is 1. And we can see that the Perceptron algorithm actually plotted a line that can separate these points, meaning that everything on one side is for one output and everything on the other side is for another output. And in cell 8, that's basically what I'm doing. I'm trying to plot all the different points that I could get, right? Those red and green points. And then I'm trying to plot the line that the Perceptron algorithm actually outputs after having learned from all of its mistakes. So this is a more mathematical perspective to look at things, and this separating line could also be called a separating hyperplane. But I think that's it for now. Thank you for watching this tutorial. I hope you got very excited and I hope it was informative. If you want more of these videos in the future, please like and subscribe and leave a comment below. Thank you.